to generate traffic at different rates, and we measured how much time it would take to pinpoint the localization of that target using our localization mechanism that is based on RSSI. So these are the results. You see that the more traffic you have that node generates, the more harder it is to pinpoint the localization of that target. We programmed these nodes with HNAME, and the results are completely different. We can see that it doesn't matter how much that node generates traffic, it will never interfere with the others, as this is obvious. So this was a very easy way to find out and to actually demonstrate how much this problem would affect wireless networks and the real-world application. So another contribution was related to real-time communications of the cluster trees. We had previously proposed works on this. We had previously proposed a time division cluster scheduling mechanism for scheduling the transmission of inside different clusters, so they will not interfere with each other. So that this cluster could not interfere with this one or that one. And also, we had already developed an analytical model for worst-case analysis and dimensioning of cluster trees to achieve to compute worst-case message end-to-end delay and routers buffer requirements. In the context of this thesis, we implemented all these required mechanisms, like the time division cluster scheduling, and we carried out an experimental assessment of and validation of the theoretical model. So we measured worst case, maximum and average end-to-end delays, buffer requirements, and we also measured the theoretical and experimental system lifetime. Sorry. Okay, so this is the MATLAB tool developed by Petr. There. to perform these computations. That is the experimental scenario I used for the experimental validation. These are the results for buffer requirements. On this example, the sink was placed at depth 2 of the tree, and you can see, so these are the theoretical, the results from the theoretical model, and you can see that your buffer requirements increase as you get closer to the sink. And on white you have the experimental results. There is a difference. I mean, the behavior is the same, but there is a significant difference between those, and this is explained by some of the limitations of network calculus, and the way it models the service curve. But Petr can explain you. He's more into that stuff. So if you have any questions regarding that, he's the right person. So all these experiments, all these validations enabled us to find out some constraints regarding the OpenZB implementation of TinyWise. By the way, OpenZB is, for those who don't know, it's 15.4 and the ZigBee implementation in TinyWise. So we found out that these constraints were mainly related to the fact that TinyWise does not support any kind of task prioritization, and the fact that it's non-preemptive. So consequences are that whenever you get an interrupt and you're going to post a task, that task is not going to be processed immediately, and if you have many other tasks in the queue, since it has a FIFO queue, it may take some time to process that. And that is not, that is okay if you have very low traffic in your network. You don't have to post many tasks to process all that traffic, but you will get into problems if you increase that traffic and if you have more stuff to do. So to overcome this problem, we start to port the OpenZigBee stack to the Erica, which is a real-time operating system. This was done in a collaboration with Retis Lab at Scuola Superiore Sant'Anna in Pisa, Italy. So far we've implemented coordinator and end devices, slot system ACA, GTS, and association mechanism. Actually, Marish Pasa is also here, is now working on this, trying to fix some of the bugs that are still on the code related to the association mechanism. This was a comparison between that implementation on Erica and the implementation in TinyWise. Okay, we had different platforms, but we tried to upgrade Flex to work also at 8 MHz. And the throughput the amount of traffic we can give out to the network is much higher when using Erica, and you can actually see that the network remains stable, which does not happen when you use TinyWise. Those are the Flex cores, which are the platforms we are working on in this quarter. So, in summary, you confirm that 15.4 and ZigBee protocols combined with commercial hardware and software platforms and with some add-ons may fulfill the timeliness and the energy efficient requirements that some of our wireless network applications may have. So, just a quick overview on the contributions. On the slot system ACA, we have some on HNAME, worst case dimensioning. Okay, this is online, and okay, that's pretty much it. I would like also to focus on the fact that we have, this is not a plate, I'm sorry Mary, we have more than 60,000 visits to OpenZigBee and 4,000 downloads of the OpenZigBee toolset. We are now in a collaboration with the TinyWise Network Protocol working groups. I'm a member of the 15.4 and the ZigBee working groups, and we're working porting the stack to TinyWise 2. We are okay, and that's it. So if you have any questions.